In this lecture, we're going to discuss generative adversarial networks, also called GANs. As inspirational example, you can look at some of these web pages. For example, this web page can generate synthetic faces of people that don't exist. Refreshing the page always gives you a new face. Of course, you can also generate cats. Let's first discuss the term adversarial training. There are multiple different meanings, or there are multiple different ways that adversarial training is employed in deep learning. One possible definition is training a model in a worst-case scenario with examples chosen by an adversary. Examples are agents playing against a copy of itself. This is a way to learn to play chess, Go, or Dota 2. There's also an area called robust optimization or robust control that you can look into. And the book below is an example for a starting point. Then, what we've already briefly discussed is the idea of training a neural network using adversarial examples. One goal of this training would be to make the neural network more robust using adversarial examples so that the network then becomes less sensitive to these examples. And now in this lecture, we'll discuss the last possibilities on this slide. This is generative adversarial networks. So to sum up this slide, we can say that generative adversarial networks are one way of adversarial training, but there are several other ways that adversarial training is used in conjunction with deep learning. We already discussed supervised versus unsupervised learning, and generative adversarial networks fall into the category of unsupervised learning. Having said that, however, when we see a lot of the variations of generative adversarial networks, there will be some form of supervision and some labeled data might be used. However, the basic form just uses a lot of unlabeled images as input. That is also one thing that makes generative adversarial networks a very attractive way of doing something with deep learning. It is because you can work with a large set of images without needing any labeled data. Also, reviewing the idea of generative modeling, what we see here on the left is some training data. And the training data is just one-dimensional, so we can plot the training data on the real number line, and that's what's depicted in this rectangle to the left. So we can see that maybe here's some gap, there's no data here, but maybe here there seem to be more samples than in other regions. And one way to do generative modeling would be to fit some form of a density function to these samples. So the fitted density function is this blue curve here. So this would be just one example. But generative adversarial networks, they will not explicitly fit such a density function. What generative adversarial networks will try to do is just use the samples as input and then generate more samples that are similar to the training samples, but there will be no density function that is being constructed. So at the end, you are not able to evaluate what is the density value of one particular image. So looking at this visualization here, there would be a data set of multiple thousand face images, for example. A few of those from this training data set are shown here. And then the generative adversarial network should generate new face images that look like the face images in the training data. Also, to again look at this graph here that distinguishes generative models. First, looking if they're doing some explicit density or implicit density, then GANs are on the right side here. That is, these GANs, they working with implicit density, so we don't have an explicit density models. And what we're doing is we're doing direct sampling. So we can look at generative modeling in general, but this is just also to discuss GANs in particular, what are they used for. So one thing that GANs have been used for is to generate training data for other deep learning models, for example, reinforcement learning. GANs have been used as data augmentation technique for other supervised learning neural networks. For example, we could generate faces for a face classifier. GANs can fill in missing data or missing labels. For example, if you have a photograph and there's a large region of missing pixels in the middle of the photograph, a GAN could be used to fill in the missing pixels. We already saw that GANs can generate images that look pretty realistic, but extending that to videos, maybe GANs could be used to generate movies, or at least smaller video sequences. GANs could be used to generate music. They already have been successfully employed to do that. And maybe GANs could also be used to generate games. So any type of content generation. GANs can be used for prediction. For example, predict future video frames given past video frames. GANs also are a popular method for outlier detection. Even though GANs don't have this explicit density, GANs can nevertheless, with some extensions, be used to determine if a model is more or less likely to be generated by a GAN. Also, it might be possible to see how easy or hard a GAN does when trying to learn certain samples. A lot of image and video processing could benefit from GANs. Super resolution is something that GANs are pretty good at, but also other forms of interactive video and image editing. For example, just a few days ago, I think Adobe started to offer neural filters to perform image editing on faces. Here is just a view of an Adobe web page to see an example of neural filters. For example, on the left there is this input image of a person, and then on the right the person has been made smiling using generative adversarial networks. Here is some other example of neural filters in action. Here's some history of face generation using GANs, and we can see that there has been tremendous progress from 2014, the original GAN paper, to 2018, when the first realistic images could be produced. Now, while in 2018 GANs were able to generate some realistic images together with lots of not so realistic images, nowadays, that is 2020, we have GANs that can pretty consistently generate images of very high quality. That means very high quality based on superficial inspection only. If you look at images more closely and you try to train yourself as a human observer to find which images are real and which are not real, it is still something that is fairly easy to do. For example, this blob artifact on top of the image here is typical for the GAN called StyleGAN, and would be a giveaway that this is a synthetically generated image rather than a photograph. One intuition that is given for GANs is the idea that evolution would train birds and insects to simultaneously improve in a process of natural competition. The insect, shown here, tries to improve its camouflage, so it is less likely to be detected by a bird, and the bird will try to improve its vision system or whatever to still be able to detect the insects despite their camouflage. What we have here is an adversarial game. We just call it game in the sense of game theory, where we have a generator that would be the insect trying to develop a camouflage pattern, and a discriminator, that is the bird, trying to distinguish the insect from the background, or in this particular case, from other leaves. Another intuition that is often used is the idea of police competing with art forgers. So, or maybe forgers that try to print fake money. So the forgers, they try to create paintings or money that looks more and more realistic, and the police try to distinguish the forged paintings or forged money from the real ones. In this analogy, the forgers would again be the generator, and the police would be the discriminator. So the basic GAN architecture is that we basically have two neural networks competing with each other. The generator takes a random number as input. So this random, so this is Z is a vector of random numbers, and many GAN papers call this vector of random numbers Z. And this is fed into a feed-forward neural network that usually always increases the resolution until it has the final resolution. And so I'm going to draw it like a convolutional neural network that has more and more spatial resolution in the tensors that the layers generate. All right, and then the final layer will give you the the image that the generator generates. So this is the generator G. And the discriminator D is looking somewhat symmetric. It's a classification network that starts with the image the same size as what the generator outputs, and then generally, as we know from classification networks, the resolution in the layers gets smaller and smaller, and at the end it maybe outputs a verdict that either the image is fake or it is real. GANs can be evaluated using the FID score or Fréchet inception distance. What we're going to do is compare statistics between images that are real and images that are fake, or images that are generated by the generator. So we will take a set of images from the training data set, x1 to xn, and then we generate new sample images with the GAN that we have trained. We'll call them y1 to ym here, and generally we would like that n and m is the same. So a good number to think about is 50,000 here. This doesn't work with very small numbers. And then we'll take the real images and the generated images by the generator, and we feed all of them into a pre-trained feed-forward network, for example, the Inception V3 model. And then from one of the last layers, we take the 2048 dimensional activations. That means for every image, for every real image and every generated image, we'll have a 2048 dimensional feature vector. And then we'll compare statistics. And the most obvious statistics to compare are the mean and the covariance. So the mean vector m will be a vector that has 2048 dimensions, and the covariance will be a matrix that is 2048 times 2048. And then we will compute the distance as follows. The mean, so mx, we denote the mean value of the images that are from the training data set. These are the real images, and my is the mean of the generated images. So this is pretty straightforward. We do L2 norm squared. And then the covariance, this may be a bit less straightforward. You would have to look it up how exactly this is justified, but the computation is pretty trivial. So we take the covariance matrix of the real images plus covariance of the generated images minus 2 times, and this is the matrix product. We multiply the two covariance matrices together. Then we take the square root. Now note this is the matrix square root, not the regular square root. So this square root takes the matrix, so this product here, and it factors it into two matrices. I'll just call them A times A, and the matrix A that can factor this resulting matrix, this will be the square root. And then we take the trace of this matrix in the bracket. Let's look at this in code. So what we have is the mean. This is a vector. This is the sample mean, and then we have the mean of the real images from the training data set. This is another vector, and then we have the two covariance matrices, sample covariance and real covariance. Then what we have here is first the cov SQRT is computed by the matrix product between the sample covariance matrix and the real covariance matrix, and then afterwards we compute the matrix square root. Now jumping to the last line, this is then the trace as we discussed, and this is trace of sample covariance, real covariance, and -2 times the covariance SQRT. That is what we computed up there. The mean also, according to the equation, first we compute the difference between the two mean vectors, sample mean and real mean, and then we compute the norm that mean diff at mean diff. This is the inner product between the two vectors, which means that all elements are going to be squared because we compute the inner product of the vector with itself. All elements are going to be squared, and then we sum up.